Let's say that we have a first order differential equation and we're trying to solve for y as a function of t. And let's say that our equation holds the form the derivative of y plus some continuous function of t that we will call here p of t times y is equal to some continuous function that we will call q of t times y raised to some real number exponent that we will call n. And if you have an equation that could be expressed in this form, then that equation can be considered a Bernoulli differential equation. Now for this example, we will assume that n is not equal to 0, and it's also not 1. And the reason for that is because if n is equal to 0, then y raised to the power of n is 1. And so that would just leave us with a linear first order differential equation. And if n is equal to 1, then that would leave us with a separable differential equation. And if you're not familiar with those, or if you need a refresher, I suggest you watch the first 3 videos in the differential equation playlist. I'll leave the link in the description. So the first step of solving this equation is dividing both sides by y raised to the power of n, which is the same thing as multiplying by y to the negative n. And when we do that, we get y to the negative n times the derivative of y plus p of t times y raised to 1 minus n, and that will be equal to q of t. The next step is to use substitution to convert this equation in terms of v. And we do that by saying that v is equal to this function y raised to the power of 1 minus n. And so now remember that y is a function of t, so that means that v is also a function of t. So when we differentiate v, on the right side we would have to use the chain rule. And so that will give us 1 minus n times y to the negative n times the derivative of y. And so to match the first term in our initial equation, we would have to divide both sides by 1 minus n. So when we do that, we get 1 over 1 minus n times v prime is equal to y to the negative n times y prime. So now we can substitute this into our equation. So our equation becomes 1 over 1 minus n times the derivative of v plus p of t times v is equal to q of t. So what we have here is a linear first order differential equation in terms of the function v. So we can solve it and then back substitute to get our solution in terms of y. So to make things more concrete, we'll solve this initial value problem. And the first step of solving this is dividing both sides by y squared, which is the same thing as multiplying by y to the negative 2. So when we do that, we get y to the negative 2 times the derivative of y plus 4 over t times y to the negative 1 is equal to t cubed. The next step is using substitution to convert the equation to a linear one in terms of v. And to do that, we will say that v is equal to this function right here, y to the negative 1. And so because we know that y is a function of t, then v is also a function of t. So when we differentiate v with respect to t on the right side, we would have to use the chain rule. And that would give us negative y to the negative 2 times y prime. And so to make this match the first term in our original equation, we would have to divide both sides by -1, and that will give us negative v prime is equal to y to the -2 times y prime. So now when we make the substitution, our equation becomes negative v prime plus 4 over t times v is equal to t cubed. So now that we have a linear first order differential equation in terms of v, we can solve it and back substitute to solve for y. So to solve this linear first order differential equation, the first step is to put it in the correct initial form. And to do that, we would have to divide the equation by -1. So when we do that, we get v prime minus 4 over t times v is equal to negative t cubed. And the next step is finding the integrating factor, which is e raised to the power of the integral of -4 over t dt, which of course is e to the -4 times the natural log of the absolute value of t, which can be rewritten as e to the natural log of the absolute value of t raised to -4. And the natural log and e cancel out, so the integrating factor is t to the -4. And so now when we multiply our equation by this integrating factor, we get t to the -4 times v prime minus 4 t to the -5 times v is equal to negative t to the -1. So the left side of this equation is the product rule in terms of t to the -4 and v. So that could be written as the derivative of t to the -4 times v. And that will be equal to negative t to the -1. And when we integrate both sides with respect to t, we get on the left side t to the -4 times v is equal to, the right side would be negative natural log of the absolute value of t plus the constant of integration. And to solve for the function v, we will multiply both sides by t to the 4th. That will give us v of t is equal to t to the 4th times c minus the natural log of the absolute value of t. So now that we have solved the linear equation in terms of v, we can back substitute and make the equation in terms of y. Now remember that we said v was equal to y to the -1. So when we substitute it, we get y to the -1 is equal to t to the 4th times c minus the natural log of the absolute value of t. At this stage, we can either solve for y, or we can actually plug in the value of our initial condition to solve for the unknown constant c. So let's go ahead and do that. When we plug in the value of our initial condition, we get -1 raised to the power of -1 is equal to 2 to the 4th times the unknown constant c minus the natural log of 2, which is -1 is equal to 16c minus 16 times the natural log of 2. So when we add 16 times the natural log of 2 to both sides, we get 16 times the natural log of 2 minus 1 is equal to 16c. So when we divide 16 from both sides, we get the natural log of 2 minus 1 over 16 is equal to c. So now we can actually plug this value back into our equation and then solve for y. That will give us the particular solution that satisfies the initial condition. When we do that, we get y to the negative 1 is equal to t to the fourth times the natural log of 2 minus 1 over 16 minus the natural log of the absolute value of t. And at this point we can just solve for y, and y of t would be equal to 1 over t to the fourth times the natural log of 2 minus 1 over 16 minus the natural log of t. And this is the particular solution that satisfies the initial condition of our initial value problem.